building an extension of a standard TLS protocol. So think of TLS. In TLS, we have a TLS client, which is a user, and TLS server, which is a website. And we add on the TLS client side additional server, which is actually a TE, Trusted Execution Environment, which helps the user to act as a TLS client and then communicate with the website. TE holds the TLS key. TE helps to encrypt traffic, sends it, helps to decrypt traffic, and tells the user, here is the response you received from the website. In the meantime, TE also sees all the traffic and then can sign, yeah, actually, I know this traffic came from the website because it was encrypted with the TLS key, which I know. And one natural question, which I would like to answer right away, is, okay, but why we're talking about TEs even? And the trivial answer is, we want to be sure that the code that runs on this server is actually honest code, which cannot be tampered with.
Does that not mean that if this TE is compromised, all of the information about the user is kind of leaked?
That's an amazing question, and for sure TEs are unfortunately notorious for leaking the data all the time. On the other hand, TEs are reliable on running the code that was uploaded there. So yes, it would be nice to not trust a single TE. We add a second TE. So now think of a picture in which there are two TEs and the user, and they all act as a TLS client, and then they connect to the website and communicate somehow. Importantly, from the website perspective, nothing changed. It looks like they're just communicating with a real user, and the website cannot tell the difference between the real TLS connection or the TLS connection that runs through Reclaim protocol. So now, back to TEs. The core idea is that we want to split the data between these two TEs the way that none of them actually learns any secrets. If they don't know any secrets, then if they're broken, no secrets will be leaked. So let us first zoom in into what's happening inside TLS to see how we divide computations between TEs. Basically, you can think of TLS as an encryption protocol, right? The data that goes between parties, it is not supposed to be seen by anyone. So TLS 1.3 uses two main encryption schemes, which are ASGCM and Chachapoly. And each of these schemes, they actually consist of two parts, which are encryption and authentication. So encryption allows us to hide data from anyone who sees the traffic online, while authentication helps the recipient of this data to be sure that it was not changed on the way. Now, the clever trick we use, which is divide these two operations between two TEs. Now we'll have an encryption TE, which will help the user to encrypt and decrypt data, and we'll have a authentication TE, which will help to compute the authentication tag. This is actually this division is the biggest insight in this story. Okay, so now we're talking about how to hide data, right? We don't want any single TE to see any data, which was the original motivation to actually split between two TEs. There is one part which is a request that the user wants to send to the website, and it can contain some secret cookie, it can contain a password, maybe some other credentials that the user doesn't want to reveal. And what's a simple trick how to hide it and still be able to encrypt is to just mask this data. So you just generate some random stream and do XOR operation with the parts which you would like to hide. You send it to the encryption.
So this
TE.
is on the plain text. And on the plain text, on the plain request, I
yes.
just XOR the private parts, send it to the TE. Okay.
Yeah, exactly. Because now we want to encrypt it, but the user doesn't know the key. So the user must resort to encryption TE to encrypt this plain text. It's now masked. Basically, you mask the data, then you encrypt the data, and then you can demask the ciphertext, and you will get the exactly same output as if you were just encrypting a plain data without masking it. So once you send the masked data to encryption TE doesn't see what's behind those secrets, masked secrets, but it encrypts the stuff. and the encrypted stuff goes to authentication TE. Authentication TE now doesn't hold the TLS key, so it cannot decrypt it back. It cannot see what was the plain text, even though it masked, but still. It holds some secrets which are derived from the knowledge of the key, but which do not disclose the key itself. The user just sends the same streams that were applied to mask the plain text to authentication TE, which they apply to demask, and now it is a real ciphertext of the real original non-masked request, and the authentication TE just computes the authentication tag, sends everything to the user, so the user is able to communicate with the website and send the real encrypted and authenticated request.
Hey, so what is the problem that we are solving with the second TE?
Great question. So now let's think of what one TE knows and what another TE knows. As for encryption TE, they know the request, where some parts are hidden, masked basically, and everything else is seen as a plain text, but everything else is not secret. There are some headers, there is some publicly available information, which is not supposed to be secret from the not a secret of the user. So when the encryption TE is attacked and let's say the data is stolen from there, this doesn't lead immediately to the leak of secrets of the user. On the other hand, there is authentication TE, which only learns some ciphertext and then computes authentication tag, which are then sent to the website. But anyway, if the authentication TE is broken and all the data is stolen from there, there are still no secrets of the user, and so we don't jeopardize the user's privacy by relying on a single TE. When both TEs, they carefully record everything they get, and then they will sign on this data, and all the data cumulatively from both TEs will help a third-party verifier to demask, decrypt all the necessary stuff, and then see that actually, yes, the user did use this masking stream, the user did send this message to the website and did encrypt it with a TLS key that was known by the encryption TE.
Got it. So again, all of this is a way to say, hey, we cannot leak privacy, but at the same time, we cannot compromise on integrity. That is, now if you're proving information that, let's say, your bank balance is so and so to, let's say, a lender, you don't want to be in a situation where the user can lie about what their bank balance is by, changing certain secrets that are on device, and that's kind of the problem that we're solving over here, both privacy and integrity. I think that's very important. Now, what about response? In the response, I do not know beforehand what the response is going to look like.
Exactly. Same masking unfortunately doesn't work for a response. As you might expect some structure, but you never know which specific byte contains your private information, your bank account number or the balance. And so here we use both TEs, and we don't want to reveal to any of them all the data or any of the data. So first of all, you as a user, you receive an encrypted response. And the first step you do, even as a regular TLS client, you want to check the authentication tag, just due to cryptographic reasons, to be sure that this data was not tampered with on the way. You just give it to the authentication TE and ask to check the authentication tag. The authentication TE verifies that yes, it did come from the real website because the authentication tag is correct. So further, authentication TE will sign on the fact that the authentication tag was correct, and meaning that a real website encrypted this response. Now when we know that the authentication tag was correct, the only step is to decrypt the response. We ask the encryption TE to just generate the pseudo-random stream based on the specification of the corresponding encryption scheme, and send this stream to the user. So now the user just stores it with the ciphertext and completely decrypts the response. So what's known to each party? User learns the response obviously and now can act correspondingly or prove something about it. Authentication TE learns only encrypted response, which is just gibberish data because they can't possibly decrypt it. And the encryption TE learns essentially nothing.
The user also does not learn the encryption or decryption key, right? So it cannot tamper with data in any ways.
Exactly. And also important thing is that for the next message, for the next block, which they need to encrypt or decrypt, this very same stream will not be applicable because it's going to be completely different.
Now, how do the third parties trust that this information was actually true?
Yeah, this is the core of the protocol. Each TE records all the data they receive throughout one session. And as for the response, authentication TE learns the encrypted response. So they just sign on the encrypted response and provide it to the verifier. Now, what does the encryption TE know? It knows the decryption stream. So they sign on the decryption stream and provides it to the verifier. What is the problem of this approach? Basically, response can contain a lot more data than we want to prove and that we want anyone to know. So we do another trick. The user just asks after decryption, after seeing what's inside the response plaintext, the user says, hey, okay, but I actually want to prove data between bytes 6 and 103. Please just give me this part of the decryption stream that corresponds only to this part of the response. Now, encryption TE just cuts this part out, signs it, and provides it to the user. And the user provides it further to the verifier with specifying the range on which to apply it. So now the verifier has a signed encrypted response. The verifier knows which bytes to apply the decryption stream. They just XOR and see this part of the response. They see only some specific data that the user actually aimed to prove. So user just performs TLS, just waiting for some help. TEs just performs more or less pure TLS operations, meaning that it doesn't matter actually what is your phone, right?
Actually, I do have this Samsung A11, pretty low-end device at this point. So this is nice to have. That is, of course, this phone can do TLS. Obviously, there's no additional overhead that is being added for any computation. That's freaking awesome.
Yeah, and connection is actually established between the real user's device and the real website, meaning that the website sees the IP address of the real user. The data comes directly. Yeah, of course, it was computed somehow with the help of some TEs, but from the website perspective, it's as pure as it can get, just a real traffic coming from a real user with no proxy or anything on the way.
That's awesome. Kirill, thank you so much for going over all of this in significant detail. Of course, the devil is in the details, so we obviously have a white paper that is out there. The link will be there in the description. And right now we are benchmarking it, getting the security audits done. So maybe in a week or two, we will have the engineers who are actually implementing this lab and Alex, who will be joining us to talk about what the benchmarks look like once we have those numbers ready. Kirill, thank you so much for joining us.
Thank you.
Awesome. See you soon. Take care. Bye.
See you.